Hello and welcome to lesson number 3 in our series on descriptive geometry. Today we're going to explore how to define lines in three-dimensional space using bearing, grade, and slope. Then we're going to try and build a principal view of our first planar surface. For our first theoretical portion of today's video, we're going to be looking at SolidWorks, and we're going to be discussing primarily the edge of the part that I've bolded here in black. As you solve problems using descriptive geometry, you are going to encounter the phrase frontal line, profile line, or horizontal line. For this video, I want you to focus on the three profile planes that I'm showing here: front, horizontal, and profile. Just as a really quick review, let's go back to the front plane, and I want you to see that the horizontal plane is represented by that edge right there. And likewise, this edge over here represents an edge view of the profile plane. If we take any line, any edge on a part, and we extend it out, we just imagine that it travels off into infinity. In general, we can be pretty sure that it's going to intersect at some point with all three planes: front, horizontal, and profile. However, if a line only intersects two out of the three principal planes, then we assign the name of the third plane to that line. Another way to say this is that if a line is parallel with one of the principal planes, then we assign the name of that parallel plane to that line. Let's take a closer look at the black line in this model. If I trace this line out, just kind of keep coming out in that direction, eventually I'm going to intersect with the profile plane. And if I go the other direction, if I start tracing up, eventually I cross through the horizontal plane. But what it doesn't look like is it doesn't look like I ever intersect with the front plane. In fact, these two things are parallel with each other. Parallel is the mathematical definition for things that don't intersect. So we're going to call this guy specifically a frontal line, as opposed to just a line. Now what that tells me, what that's useful for in descriptive geometry, is it's like a sort of code that tells me very quickly that if I look in the frontal plane, I'm going to be seeing the true length of the black line. True length is another term that you're going to hear very often. It means that when I measure the line on the computer in that view, that's going to be the actual length of that edge on the part in real life. The thing about descriptive geometry is that the computer is constantly trying to lie to you about lengths or angles, and it is so easy to get fooled. For this reason, we're going to put the letters TL next to a line that is in true length. As an example of the deceptive nature of lines that move in and out of true length, let's go back to looking at that black line. If we look at the frontal view, we're seeing 100% of the total length, the true length of that line. If I move up to the horizontal view, the black line ends up looking shorter. And if I look to the profile view, the line still looks just a little bit foreshortened. I want to show you in SolidWorks. We're going to use the measure tool here. And I'm going to actually measure this line from that center point, which we'll call the beginning, to that guy, which we'll call the end. And you see that three measurements actually pop up: a black one, a red one, and a green one. The black one represents the actual true length of that line. The green line here, and this is actually kind of cool, SolidWorks is building a reference profile line. I can tell that it's a profile line because it looks like the green line is parallel with the profile plane. And you can tell that this guy is shorter than the true length line. It's always going to be true. Any view that's not true length is going to give you a shorter measurement. Likewise, the red line down here is a horizontal line because it's parallel with the horizontal plane. If we go back to the profile view, you can only see green there. If we go to the horizontal view, I only see red. Notice that, remember, neither of those represent the actual measured distance of that line. The only thing that truly represents that is the measurement in black here, the actual true length of that line. So the last thing I kind of want to draw your attention to with our whole measurement triangle thing that's going on is that we sort of have a right triangle Pythagoras sort of thing going on here. And it makes sense that these measurements that you're getting in other views are always shorter than the true length, because the true length represents the hypotenuse of that right triangle. The next theoretical idea that we need to talk about, let's close that command down and return back to an isometric view, is the idea of a true angle. So remember how a moment ago I told you that in descriptive geometry you can't really trust a measurement unless it's been specified to be in true length? Well, there's also angles that kind of operate according to the same or similar rules. So let's take a look at the frontal plane again. And I'm going to slowly rotate towards the profile view. I want you to pay attention to the angle that's formed between the black line and the horizontal plane, which is represented by the edge right there. I want you to notice that the angle starts to get smaller and smaller, and then starts to get bigger until it reaches, eventually, 90 degrees. If we return back to the frontal plane, and I do the same thing, but this time you pay attention to the black line, the angle between the black line and this edge, which represents the profile view, you'll notice that the angle gets smaller and continually gets smaller and smaller and smaller until it reaches 0 degrees. One of these angles would be considered to be the true angle, and we define it like this. If you're looking at the true length of a line, and it absolutely has to be the true length, and you also simultaneously have a view of only the edge of the plane that you're trying to connect to, kind of like how this line right here represents the horizontal plane and this line right here represents the profile plane, those are edge views, then the angle, if we were to measure the angle between the black line and the horizontal plane, or the black line to the profile plane, those would be considered true angles, the true horizontal angle, or the true profile angle. Now, we can take a look at an alternative view here, because we're still looking normal to this black line right here. This line is still in true length. But could we measure the angle between this line and, say, the horizontal plane? Well, no, we couldn't, because we don't have this guy in an edge view right now. So if you were to measure this angle to here, well, you'd get an incorrect angle. You'd get a foreshortened angle, kind of like how with a line we were getting foreshortened, smaller lengths instead of the true length of a line. The same is true if we were to try to measure the angle between this black line and the profile plane here. For the same reason, you don't have an edge view of the profile plane. We need both the true length of the line and an edge view of the plane that you want to measure to before we can say that an angle is called the true angle. Okay, whew, that was quite a bit of theory we went over. So let's move over to an example where we're going to be trying to find the true length of a line and also the true horizontal and profile angles. So I have the line RS here in a horizontal view and a frontal view. And I want you to notice that the difference between these guys is really, it's the same thing as over here, except we're just not showing the box. We're really just focusing only in on that black line that we've been working with so far. So I know sometimes the problems can seem like really abstract, and honestly, that's just so it doesn't get as confusing. Believe it or not, trying to draw all of this with these shapes can get a lot more confusing. So we only try to work with just the piece we're trying to get information about. In that case, that's only this line. So the first step, whenever we're trying to solve a problem, is we start with folding lines. So move myself into the folding line layer. I'm going to draw a folding line right there. I need to define that folding line. So I'm going to borrow some of this text right here. Up. Place that text right there. Maybe that one a little bit lower. Yeah, it doesn't look too bad. So now we know that this is a folding line between the horizontal and the frontal plane. Now the next thing we need to do is we want to get the true length of this line. So we don't know for sure if this line is in true length. It could be, could very well be, but they haven't written TL next to that line, so we can't trust that that line, if we measured it, was in true length. So we're going to have to force it to be in true length. And the way we're going to do that is we're going to create a new view. I'm going to start by copying this line. Pick it up, just move it out just a little bit. I'm going to take it and move it onto the folding line layer. I'm then going to pick up these letters right here, drop them right around, somewhere around the center there. And then I'm going to rotate them to pretty much match with that line, so everything is nice and neat. And we'll do one last little bit of alignment right there. Since this over here is the horizontal, come on, there we go. That's the horizontal side of that folding line, and this is going to be an auxiliary view, so we're going to call it 1. Next step is we need projection lines, so I'm going to move to the construction layer. I'm going to open up the line command. I'm going to draw a line so that it's perpendicular to that line right there. I'm going to pick it up and move it over there. Then I'm going to copy it over to the other point S. Perfect. I'm going to type LEN for lengthen, DY for dynamic, and I'm going to stretch out that folding line just a little bit so that it's bigger than the object. The box is bigger than the object it's supposed to be containing. Now our next step is we need to create offset lines. So I'm going to start by typing offset for the offset command. And we're going to go 2 views back. This is the view we're interested in, so that's 1 view back, 2 views back. So we're going to work down here. That's point S to that folding line to there. I'm going to drop a little circle right at that intersection, and that's going to be our point S. Do the same thing for point R to the folding line, and from the folding line out to where R should be. And a little circle for that point. We're going to move over to the object layer. We're going to draw a line from the center of that point right to there. We'll delete the circles. And we're almost there. I'm going to type trim for the trim command, use that guy as my boundary, and get rid of those. And we're ready to borrow some text. There's the point S. There's the point R. We'll change the superscript to a 1 since we're looking at auxiliary view 1. And we're going to add one extra piece of text. We're going to add a TL for true length. I'm going to start the rotate command. Pick this guy up and put it right there. True length. So it's interesting to me in descriptive geometry that we don't actually dimension this guy right here. We just say it's in true length, but we don't actually report a number or anything for it. We're more interested that everything is proportionally accurate, meaning that if something is half the size of something else in real life, it should always look like it's about half the size on paper. And that's kind of frustrating because in a minute we're going to dimension an angle and it's going to show up as a number. It's very, very strange. I don't know why the convention is the way it is, but it's probably what your teacher's going to do. And it takes a deeper knowledge, a deeper understanding than mine to explain why that is the way it is. Now, we can snag something else that's important. Because the line that we're looking at, R to S, is in true length, and we have an edge view, of the horizontal plane, remember each of these folding lines represents an edge view, we can pick up the true horizontal angle from the line to the plane, 27 degrees, which should be on the dimension layer. 27 degrees, brilliant. We'll boot up the length, dynamic, turn off the snaps, and we will shorten the extension lines just a little bit. Projection lines, really, instead of extension lines. Alright, so that's 2 objectives down. We need to get the angle between the line and the profile plane. In order to do that, we need to build a profile view. So we're going to return back to the folding line layer. I'm going to draw another folding line. Here to here. I'm going to pick these up, copy them. Place them approximately there. Rotate them. That time it worked. That's good. This is the frontal view, so we're going to leave that as an F, and this H becomes a P for profile. And we are ready to go. We'll move to the construction layer because we need some projection lines. And we will draw 2 projection lines. Time for offsetting again. In order to offset, we need to create 2 views back. This is the view I'm interested in. 1 view back, 2 view back, so we're going to be offsetting from this view right here. I'll type offset for the offset command. We'll do S first, since that's what we've been doing this whole time. So from S to the folding line, and then from the folding line to the point S. That's the point S. I'll track it along, and that means that intersection right there is where the point S is going to be. We'll do the same thing for the point R. From point R to the folding line, from here to here. R to the intersection. That's going to be point R. Change over to the object layer. Hey, we have a profile line. Some quick trimming and we are all set. Replace that F with a P for profile. And now we will shorten up the projection lines. Just a bit. There we go. Now, it'd be really tempting to just measure from here to the profile plane, because we got this in edge view, right? But that would be a mistake. Remember, we need 2 things to be true in order to measure a true profile or true horizontal angle. We need the line to be in true length, and we need an edge view of the plane that we're trying to measure too. So we're going to have to repeat the process that we did before over here. We're going to need to make 1 more view. So I'm going to pick this guy up, I'm going to copy him, move him out just a little bit, and I'm going to move that line to be on the folding line layer. I'm going to pick this up. I'm going to copy the text and bring it over here. Rotate it. It's usually good to do this just every time you're picking up and you're making a new folding line or you're making a new line. It can be really tempting to try and do all the object first and all the projection lines and not do it systematically. And it looks like it takes more time, but organization is really your friend here. Trust me on this one. Take your time and define your folding lines every time you make one. Oh, I turned back into an object line. That's interesting. Back into a folding line. Take your time and define as you go. It'll save you time in the end. So the next step, we go to the construction layer. I make a perpendicular line. Pick that bad boy up. Move him over. Whoop. Move him over here. Copy and bring him over here. And we're ready to go. Now we're ready to offset again. So we're going to go, this is the view we're interested in, so we hopscotch over, one view back, two views back. We're going to be doing our offsetting from this view right here. So this time we'll go from S again, there to there. From there, out. Hoo boy, it's all the way out there. That's pretty crazy. So we'll take that guy right there, and we will lengthen it. Again, dynamically move that guy out, and that's going to be the point S, right there. We can delete that now. Offset again, this time point R to folding line, and away we go. That's our last point right there. We'll move to the object layer, and we'll draw a line and connect the two. And we're ready to copy some text. Point S traces forward to arrive at point S. Oh, I forgot to even redefine these. This guy over here should be a P for profile. This guy over here should be a 2 for auxiliary view 2, because we already used auxiliary view 1 over here. Even worse. Can't even read that text right there. Sloppy drafting is what that is. So we'll move that guy down there. Fix that guy up. Copy this point so it kind of sits. We'll put it over there this time. And we'll adjust the superscript so that it reads as point 2. Type len for length, dy for dynamic, and we will just shorten those lines up, those projection lines, just a little bit. Now, the whole reason we were doing this was so that we could get the true length of this line, which means that we need to note that this guy's true length. So we're going to take that, we're going to copy that, bring it down towards the middle, just that, true length, and then rotate it so that it matches this guy to that guy there. That's all nice and neat right there. So now that that guy's in true length, we're ready to pick up a dimension. And the reason I know that is because I want a profile true angle. I have an edge view of the profile. Again, these folding lines represent edge views, and I have the true length of a line. So I'll go to my angle dimension command, and I'll dimension from the line to my plane. And I get 54 degrees. And there you go. That is a completed solution to the problem. We have found the true length of the line. Again, the number doesn't actually really matter. And we've also found the angle of that line to the horizontal plane, and the angle of that line to the profile plane. Alright, now let's talk about bearing, slope, and grade, which is going to be another way for us to define the position of lines in three-dimensional space, but we're going to be using angles to define stuff. So for this, I've drawn a really simple model. I've drawn a little red line right here in 3D. You'll see that it passes through, if you extend out here, it passes through the horizontal plane, through the profile, and through the front. So it's a regular line. It's not anything special like a frontal or a horizontal line. Now, I want to show you first what it means to have a bearing. All lines have a bearing, all lines have a slope or a grade. You're going to find out later that a slope and a grade are really the same thing, just noted a little bit differently. So let's look at the bearing. The bearing is something that happens only on the horizontal plane. It doesn't happen anywhere else. So I've drawn an additional sketch here on the horizontal plane, and let's go ahead and, it looks like it doesn't really line up. But if we take a look at the top plane, yeah, boom, lines right up with that red line right there. And what the bearing says is the bearing is an angular relationship to the line from some sort of established direction. Typically that's taken to be north, and north is typically taken to be the top of the drawing. So if this were the direction of the top of the drawing, then this section of the line would be north, this would be south here, this would be east over here, and this would be west. So depending kind of on which point we started from, this point down to this point, or this point over to this point, we would note this a couple of different ways. First, we could say, starting from north, say we were going from this point to this point over here, I'm sort of traveling in a northern direction, and I'm going towards the west. So I would say north, 65.49 degrees west. So it would be towards the west. And that's something that you'll see later later as we do AutoCAD drawings. You'll see that, and I'll mention it as we run across it. I'm not going to do it in SolidWorks because that's just going to waste too much time trying to put text on stuff. Now, another way that we could do the bearing is if we were going from this point forward, we're kind of traveling south and to the east. So we're going to say south, 65.49 degrees east. And those are equivalent directions. They're equivalent in magnitude, but it's almost kind of a difference in vectors from, from the left to the right or from the right to the left. Depends on how we write it. Conventionally speaking, when we do bearings, we start on the north axis, the top of the drawing, and we move to the line in the shortest amount of degrees. Typically, we want an amount of degrees that's less than 90. So it would be okay to go from here to, up to here until you got to 90 degrees, and then you'd probably have to switch to like south or something, or you'd have to go north this many degrees west. Point is, we start from north, typically, most people do, but you don't strictly have to, and you want this degree amount to be less than 90 degrees. Okay, let's turn off that sketch and return back to our isometric view. Now, let's talk about what it means to have a slope. You're familiar with the idea of a slope from math. The slope of a line is the ratio of its rise over its run. In descriptive geometry, we're going to have a new definition for the slope. Even though it means the exact same thing, the slope can be taken to be the true horizontal angle. And we've already done an example that involves that. The slope is really the angle of this line up to that plane right there. I'm going to show you how an incorrect understanding of that could mislead you a little bit. If I turn on this sketch for the front from a slope that's on the frontal plane, drawn right on the frontal plane. I've drawn just a standard 100 units and then connected a vertical line right here with a line that's sitting coincidental on top of that red line. And then I've just asked SOLIDWORKS what angle that comes out to be. And SOLIDWORKS says, well, that's 24.09 degrees. If I instead looked at a slope from the perspective of the profile plane, and I did the exact same thing, of 100 units this way, a line that lines up with my red line right here, and I asked SOLIDWORKS, hey, what degree is that? It says 44.4 degrees. Those don't agree. There can only be one slope to a line. So what's going on here? Well, remember from our previous example that if you want the actual slope of this line, you can't look at it from the front plane or from the profile plane because you're not getting the true length of that line. You absolutely have to have that true length. So if we go look at one more sketch, there's a plane that lines up and is going to give us the true length of that line. And if we look normal to that guy, we go out 100, there's the actual angle, 22.14 degrees. That's the slope. This is another way of writing the slope, and it's a special way, and it's called the grade. It's you can think of it as like a dy over dx sort of situation. You're going to go out a run of 100 units, and then down however many units it takes to meet up with that line, and you're going to call that the grade. And you're going to see a little bit as we move into an example. So that's an example of what the bearing, slope, and grade of a line. And any given line has a bearing, has a slope, and it has a grade. The important things to take away are that the bearing happens only on the horizontal plane, and the slope happens only if you're looking at the true length of the line and you have an angle between that line and the horizontal plane. So it can happen on any, it could happen on any plane that is 90 degrees off of the horizontal, like the front or profile, the back plane. So now let's move into our AutoCAD example. We want to draw two lines. It says that line AB, that's this guy right here, has a downgrade of 30%, which means that for every 100 units we go over, we're going to go 30 units down. And the line AC, so this guy, has a downgrade of 40%, where if we go over 100 units, we're going to go 40 units down. We're trying to complete the front views, and all we're given is this little lonely point right here. It's not much to go on. So, starting up. First thing we're going to do is we're going to make a folding line. And we'll place it right in between the horizontal and frontal views. I can tell that this is the horizontal view because of a little subscript H right there. And I know this guy's definitely a frontal view because it included that F right there, that superscript F. Alright. Now, the next thing we're going to do is we're going to pick off one of the... Oh, I forgot to label this guy. Copy this text. Alright, that's better. Now, I don't want to focus on the line A to B first. I want to focus on the line A to C first, and there's something particular about it. The line A to C is a frontal line, which means that whatever it is over here, whatever the line ends up being over here, that has to be the true length of the line. You may not be able to see that quite so clearly, but if you take enough time and you think about it, you'll remember from a previous model in SOLIDWORKS that we were just looking at that if this was parallel with that plane, then this was automatically true length when I looked at the front view. This is the front view here. These two things are parallel. This is the edge view of the front plane, and this is the edge view of the line AC. These two things are parallel to each other, which means that down here, I'm automatically guaranteed to get the true length, even though I don't know what that number is. Because I have the true length, I can make a statement about the grade of it, of that line, AC. I know that if I go 100 units, oops, we'll go to the text layer. I'll try that one more time. I'll put a rectangle right at the center of that point. I'll type DIM for dimensions. I'll specify the length to be 100, and then I'll specify the downgrade of AC to be 40 units. I get a rectangle looks like that. And I destroy my rectangle. There we go. So there's going to be a line that connects the point A, passes through the point C, and arrives somewhere over here. That's going to be the grade. Now, it's not actually this long. If we go to the construction layer and we pick up a projection line, you'll see that this line is only this short. So we'll take and we'll trim all the extra material off. Now the way that we note a grade in descriptive geometry is with a triangle. Kind of like the triangle that I was drawing over here in SOLIDWORKS to try and hint to you at what was coming. I drew these big, massive triangles over here. This 140 thing, that's what I'm referring to. We have to do the same thing in descriptive geometry as well. The quickest way to do that is we're going to pick up the triangle, we're going to move it, and we're just kind of going to drop it right about there, and then we're going to trim away the excess. Good. Now we're going to add some text to that. We went over 100 units, and we went down 40. My teacher used to harp on us that it wasn't about the size really of the triangle, and it was more about the proportion. The proportion's really easy to keep track of. If you just keep that rectangle around and then slide it up and trim off the rest, you're automatically guaranteed that the proportion between these two lengths is correct. Whatever you do, don't try to randomly just draw like two lines in here and just call 100 and call 40 or something. That's not quite the same thing. It'll be out of proportion, and your teacher will be very upset with you, as he was so often upset with me. Now, the next thing that we need to do is we need to pick up a front view of A to B. A to B is a lot harder because we're not sure this line is in true length. If I come down here, I'm not guaranteed the line's in true length, so it's not like I can do the same thing I did over here for the line AC. I can't just pick up and do the same thing over again. So we're going to have to do something a little bit trickier. Let's go ahead and copy the folding line right there, and then I'll rotate it. I'll do that so it matches up with that guy. So now it's parallel with that. I'll type LEN for length, DY for dynamic, trim that guy just a little bit, and move my identifier right to the middle of there. This guy should be an H since it's on the horizontal plane. This guy is going to be a 1 since we're going to have to make an auxiliary view. Now, because this folding line is parallel with this line right here, I'm guaranteed that whatever view I get out here is guaranteed to be in true length. But I don't have any points over here to pick up or offset. Well, it's not entirely true. I have 1 point, and that's actually the point that we're going to have to work with. So here's what we do. Offset. I'm going to pick the line A, pick the point A, rather, and to that folding line. And then from the folding line out, we'll go to the construction layer, and drop that point right there. Now, this point right here, that intersection is the point A. So now, I don't know what the orientation of the line is or what its length is, but I do know what its grade is. Because I do know that the line is in true length somewhere in this box up here. So I'm going to type UCS for Universal Coordinate System, and then I'm going to type OB for Object, and I'm going to line our coordinate system up with our folding line right here, and I'm going to draw a rectangle again. Going from this point right here, and making sure that we are on the text layer, I'm going to type in 100 and then 30. Oops, didn't work very well for us. One more time, starting from that point, DIM first for dimensions of the rectangle, 100 and then 30 down. This represents the grade of our intended line from A to B. Now again, I don't know how long it is, but I do know that it has that grade, because that's the true length of the line. And in fact, I should do that over here. I should pick up this guy over here and say that it is a true length line. So now I can reset my coordinate system, type in UCS, then type W for world. I can put a note in to note that this line is true length. Now I can go back to the construction layer, pick up that line right there, and go through here. We'll trim off a little bit of excess right there. And that's the actual length of our line. It has the same grade. It has true length. And we're almost there. Now, we'll pick this line up, or the rectangle, and we're going to move it right about there. Take this guy, I'm going to type trim, and I'm going to trim away the rest of the rectangle. Copy some text. This will be 100. This guy will be 30. Rotate that so that it matches up. You don't have to always do that. I do, because it makes things look neater and gives your teacher less of an excuse to throw you over the coals and take away some of those points. Now we'll label up that point B. Call that one point A. And now we're ready to project from auxiliary view 1, which that superscript should read 1, down into the frontal plane. So now we'll take the, okay, we're in the construction layer, that's fine. Straight down like so. And now I will offset from point B to the folding line, and from the folding line in, from that point to A. All that remains to do is a little bit of cleanup. So let's type len, dy for dynamic. We'll shorten the lines of projection, and we'll also shorten the won't let me change that. So what we'll do instead is I'll offset this line. We'll offset it by, say, 1.5. I'll go that direction, take that, I'll trim, remove those lines, and remove that offset line right there, and now you have no, your grade doesn't actually touch the object. Thing to do, we will offset again. We'll offset that object that direction, engage the trim command, cut that triangle back just a little bit, and we are done. So here's what we've done. We started with a view that was just horizontal. We recognized that this guy, A to C, was a frontal line, which we exploited to create the grade and develop the front view. For purposes of anal retentiveness, I'll make sure that my true length designation lines up with the line A to C. Then we had to build an auxiliary view of the line A to B because we didn't know if this was in true length, so we had to force it to be in true length. Then we use the grade, which we noted with this funny looking triangle thing, which came from the actual dimensions of the rectangle that I built. And then we tracked it back into the front view and create a view of line A to B and line A to C, which is what the problem asked for us to do. And that's going to conclude our second example for today. Okay, for today's final example, we're going to be taking a look at a two-dimensional plane, and we're going to be trying to create a top view of that. So in this problem, we have a full plane, A, B, C, D, E, and then we have a couple of points, A, E, and C on the horizontal plane, this all on the frontal plane. I drew a little model here of what we should be expecting to see. So the plane kind of looks like a rectangle with a triangle cut out from underneath that, and if we kind of look at it that-ish way, that's sort of what we're seeing down here. And if we get a top view of that sort of thing, we're going to end up with kind of like an underside look at that guy right there. Because I can't tell the orientation in AutoCAD, the top view really should just be looking down at the, should be looking down, and we should be expecting to see something like this, but that's not normally how I would think of that as the top view of that object as a draftsman. But this is because it's a homework problem, and not because it's real life. That doesn't mean it's important to do, though, so let's get it done. First thing we want to do is Put up the object layer. I'm going to connect points A, E, and C, because A, E, and C are connected in the frontal view. So right there, A to E, E to C, which means they have to be connected up here too. Now, we need to worry about point B and D. Those are the things we really don't have defined. So we're gonna play a nice little trick on the computer here. I'm gonna go into the construction layer and I'm gonna connect line A, point A to point C, and I'm gonna connect point B to point E. Up here, because A and E are now connected, or because A and C are now connected, I get to connect A and C up here. And I'm doing so with construction geometry, which I'm not going to shorten in the end. Now, if I just make a projection line and drag straight up, now I have the intersection between the line AC, this projection line, and the line B to E, which means that the line B to E has to be somewhere along this trajectory. It has to pass through this point and this point, because down here it passes through that point, E, and that intersection right there. So before we go any further, I'm going to copy that line. I'm going to drag it down here. LEN for lengthen, DY for dynamic, and we'll just kind of slide that line up a little bit. And now we will connect point E with that intersection right there. And here's a neat little trick for you. I'm going to type in FILLET for fillet, and I have the radius on my fillet set to 0, and I select both of this object and this object right here. They actually zoom out to meet each other, which is pretty cool. Because this is a projection line, both of these are projection lines, I'm going to type LEN, DY for dynamic. I'm going to shorten them a little bit. However, these guys, I don't shorten. That's because I actually needed these to make an intersection right here. In fact, actually, probably means I should have this guy connecting with these points right here, since I need a touch. I need these lines to touch each other in order to establish that as an actual point. And I think the same goes for here. But from here, I'm extending from the point B, and I'm extending from this intersection right here. So that guy should probably also be touching there too. But that extension, that gap right there, I think is okay. So we'll pick up the text for point B, copy it, and move it right over here. Alright, so now we'll go to the object layer, and I can connect point B to point C, there to there, and that's all I get. Okay, so now we need to find point D, and we're going to play the same game again. This time I'm going to lengthen this line, A to D, right here, and I'm going to pick B to D, and I'm going to lengthen it there to there. Now remember, I'm only doing this just for a moment. I want to pick up, I'm really interested in these intersections right here. So I'm going to copy, paste, and I'm going to there. And I'm also going to put one right there at that intersection. Then I'm going to trim those lines back so that I don't get confused about what was what. We'll go back into the construction layer and we will connect make that geometry be construction geometry. Now it's getting kind of messy, and that's okay. There's going to be a lot of lines. There's just always going to be. So don't panic about that too much. Now, this is the intersection between A, D, and a point on line BC. So that's that point right there. So we'll connect line A with that intersection that we made. So line A with that guy right there. Boom. We'll drag this guy down, cause an intersection there. This is an intersection. This line came from an intersection on line A and E. Bring that guy there. And it is a line that connects B and D. So, to that intersection right there. And right where they intersect, that's going to be point D. So, open up the trim command. This guy. This guy. Whoop. One more time. Trim. Trim. Nice. And we'll pick up point D. Copy it to the new view. Now, because these are extension views, they actually are part of the solution, as my teacher used to say. We're going to leave them connected to the lines that they're projecting to, since we need them to establish a sort of point. We need them to establish a point for geometry. We can't just kind of randomly say, oh, this one connects here. That's not very clean, so we'll move that point maybe over there. And there you have it. There's a top view of the plane figure A, B, C, D, E without any folding lines, without anything whatsoever. And this is going to become a theme as we solve problems in the future, is we're going to start dividing up lines. We're going to start drawing very particular construction lines and then taking those points into new views. And that's something that we're going to discuss further. But that's going to end it for today's video. See you next time.